Hi, this video is about rotational motion and energy, the kinetic energy of something that's rotated. Section 9.4 in Young and Freedman's University Physics. Okay, so what is the kinetic energy of a rotating particle? Well, let's start out easy. Let's say that you have a particle on a bicycle wheel that's rotating. What's the kinetic energy of that particle that's rotating? Well, we know that the velocity of that particle is the radius of the circle times the angular velocity. That's from the previous section in the chapter. Now, if kinetic energy is 1/2 mv squared, got that from a much earlier chapter in any physics book, then we substitute for the v. So if v equals rw, then v squared equals r squared omega squared. I'm sorry, it's really an omega rather than a w, but you know what I mean. So that is the kinetic energy of that particle on the wheel is going to be 1/2 m radius squared omega squared, where omega is the angular velocity. Okay, that's fair enough. Now, what physicists have done in their infinite wisdom in the past is to separate out the 1/2 and the omega square and isolate this mass times the radius squared element. Now that works fine for a single particle, but what if we're talking about a solid object, or at least an object that is somewhat three-dimensional? What we're going to find is that we can take the sum of all of the individual points everywhere in that solid object. Let's say it's a sphere. Then if you were to take the sum of all of the point masses in that sphere and all of the different radiuses in that sphere and add them all together, we're getting to a kind of calculus here. And the last section of this chapter actually talks about integral, the integrating of integration in calculus is the adding up of a kind of an infinite number of mass, like masses in this case, times radiuses. In calculus, we write that in summation notation. So we can say that this is the sum of all the masses times all the radiuses squared, and that I, basically, that I includes in it all of them. The I means all of them. The infinite number of infinitesimal little point masses that make up that solid sphere or whatever. And physicists call this by the letter I. This sum, this integral, this sum of all of the point masses in whatever it is that's rotating. Now, it may not be a sphere. On the next slide, I'm going to show you, they've already done your work for you, kind of all these I's added up. And they call this I, this sum of all the masses times the radiuses squared, the moment of inertia, which is kind of a confusing term. I wish they'd have called it something else. But basically, it's all of this mass radius squared combinations that basically create a capacity for rotational inertia. That wasn't clear at all, wasn't it? It's just basically all this stuff, all the stuff that's going to be rotating. And you're going to be able to take that. It's for a particular kind of object. It's a certain amount of stuff that you have that's going to be rotating. And if you take half of that times the angular velocity around the axis, wherever it may be, squared, that's going to give you the total kinetic energy of whatever it is that's rotating. I know that's a little hard, but several of the examples in this section have to do with unwinding cable. That may be a cable that has a block or a weight coming off of it. And some of the questions have to do with, well, like how fast is that block going to be right before it touches the ground, or how much kinetic energy is it going to have, how much kinetic energy is it going to have right before it hits the ground. And so you have to add up the kinetic energy being generated by the pulley there and connect it to the kinetic energy of the block, and you have to add those two together. And so there are instances in these sorts of pulley situations and others where you want to know what the kinetic energy of a rotating mass is, something that's rotating. And the way you do that is there is this moment of inertia or rotational inertia capacity that this object has. And when you stick a rotated around an axis, then if you take half times the angular velocity squared times this moment of inertia, you're going to know the kinetic energy of that pulley or sphere or whatever it is. Now, like I said, these are somewhat constant for particular kinds of objects, because the mass times the radius squared taken in sum is going to be the same, no matter how fast it's going, as long as you're not approaching the speed of light. So, basically, on page 299 in Young and Freedman, they give you a bunch of examples. So, if you're talking about a rod whose axis is in the center, they've already done the integration for you. They've done the math, and basically 1/12 of the mass of that thing times the length of that thing squared is going to tell you what the rotational inertia is for that rod, so that you can figure out its kinetic energy when it starts spinning. Let's say that the axis is on an end, and the rod is spinning around an axis. Then it's going to be 1/3 the mass times the length squared. Again, you don't have to. This is a matter of memorization. At the end of the chapter, we'll talk about integrating to find these things, the hard work that got us this far. But really, the scientists have long done this math, and there's a list on 299 of basically what the moment of inertia is going to be for these different kinds of objects. Let's say it's a board, a rectangular plate with an axis in the center. Then it's 1/12 the mass times the sides, the sum of the sides squared. Let's say it's that same rectangular plate, but it's the edge that it's rotating around, or the edge is rotating of the board. Then it's 1/3 the mass times the length squared, and so forth. Hollow cylinder, a solid cylinder, a hollow cylinder without much of a wall, a solid cylinder, solid sphere. I'm sorry, this one's a solid sphere. And then the last one is a thinly walled hollow sphere. So that second to last one should not be solid cylinder, it should be a solid sphere. So you get a sense here of, by knowing this kind of capacity for inertia, I wish they'd have called it that, a capacity for inertia for different shaped and sized objects with a axis running through them. The kinetic energy of whatever this thing is going to be half times that capacity for inertia times the angular velocity squared. There is one final thing in this chapter, and that is, if the mass of a pulley cable is not negligible, you have to also consider the gravitational potential energy of the cable. What is this about? Well, this has to do with some of the pulley problems that they're doing as examples here. So you had the kinetic energy of the pulley that you had to figure using the moment of inertia equations I just talked about. You had the kinetic energy of the block that's falling, but in their initial examples they considered the weight of the cable itself to be negligible. But let's say that the weight, let's say that the mass of the cable is not negligible in this pulley cable block experiment. Well, they derive an equation at the end of this section that the potential energy of that cable is its mass times the gravitational constant times the center of mass. cm is not centimeter here; it's the center of mass of the length of that pulley, wherever the center of mass is for that pulley in relation to the way you set up this problem. Then that, wherever that is, times the gravitational constant times the mass is going to give you the potential energy of that cable. Key to these sorts of equations is the conservation of energy. So the kinetic energy of the block and of the pulley and the potential energy of the cable, all of that at the beginning of letting the pulley go has to be the same as the total energy, right before it hits the ground, and so forth. Well, complicated chapter, but you can do it.